I'm going to talk about principal components analysis today. Principal components analysis is one of many multivariate methods to understanding data sets with lots of columns of data, with lots of measurements. And it's a means of reducing data down to a few dimensions and looking for patterns. So it's an exploratory type of analysis rather than a hypothesis testing analysis. However, when you do a principal components analysis, you end up with values, principal components in your data set that then you can use in some sort of hypothesis testing analysis like analysis of variance. So here's an example of a kind of data set that you might use principal components analysis on. Principal components analysis works really well with data like measurement data, measurements of body size, shape, etc. Anything where you're measuring something that varies quite a lot and is continuous variables. Tends to work best also with variables that are normally distributed, but principal components analysis is found to be pretty effective even when data aren't perfectly normally distributed. So here's an example data set. These are measurements of a small mammal species that's common in Washington called a vole. Three species of vole listed here. And the measurements include the length of the animal, their body length, so this is the length from the snout to the rump, the tail length, the foot length, and ear length. Okay, so somebody might take these sorts of measurements to look at how those body measurements change across an environmental gradient or differ between species. These differences in the shapes most likely reflect differences in ecology. For example, a vole with larger ears compared to its body size than another vole might be hunting using hearing or moving in its environment, relying more on its hearing than voles that may have a stronger sense of smell, or some may have different sizes in their, or different aspects of their foot morphology that might tell you something about their ecology. Now you could look at each individual trait and analyze it and see how they differ. But really, if you want to understand how voles change and shift in their body shapes, something like a principal components analysis can be very, very powerful, because what it does is it reduces these multiple measurements to something that's in one or two dimensions and explains more of the variation in your data than any one of those measurements can. And you can get output from principal components analysis that tells you which of these variables, sometimes it's a combination of them, explains the most variation in the data for each principal component that you get. So it can be a really useful analysis. Now, how does it work? Well, it's essentially, complex math is behind it. It involves the generation of correlation and covariance matrices, but it's very similar in its approach to simple linear regression. So if I wanted to look at the relationship in this data set between two of the measurements, just pull up a graph builder here and jump. Say I want to look at the relationship between the total length of an animal and its body length. Okay. I'm not too surprised to find that there's a scatter that's looking fairly linear and positive, so that as body length increases, the total length from the snout to the tip of the tail, so does the body length of the animal, okay, from its snout to its rump. Those are correlated variables. However, you might have voles with very long tails and voles with very short tails, so there may not be a perfect correlation in that kind of data. I can fit a line through that, a line of best fit, and this is the line that minimizes the distances of all of these points from itself, and that's the line that has the greatest explanatory power. If I want to, I might not find that that's a very interesting variable to measure, so I might plot, say, total length by foot size. Maybe foot size is independent of body size. Turns out, well, it looks like there's still a positive relationship. And when I put a line of best fit through this data set, there does look to be a relationship between foot size and body size, although it is not as close a fit as we found with body length and total length. Okay, so you could do this, you could do multiple scatters, but principal components analysis, you can imagine also plotting this data in three-dimensional space, say total length by foot size by body length, and mapping those points out in three-dimensional space, and then drawing another line through that would be the line of best fit. But once you get to 4 or 5 or 6 measurements, it's very hard to conceptualize how you might look for those patterns. But you can use complex math to actually generate a new coordinate system for that data set and find vectors, what they call vectors, which are lines that have basically a starting point but no ending point, that have the highest explanatory power. And those are your principal components. So I'm just going to show you an example of a publication that used principal components analysis to look for groupings in a pattern or in a data set. Okay, so this is a 2011 paper. I'm going to scroll to the top that looked at genetic data and song data of a species that back then was called the winter wren. Back then, winter wren was thought to be a whole Arctic bird species, so it was found around the northern areas of the world, found in Eurasia, also found Europe and Asia, and also found in North America, but there were distinct subspecies. There was the Eurasian subspecies, the species that we find in the Pacific Northwest, and then an eastern subspecies, all considered winter wren because by their appearance, they look almost identical. However, people wondered if there was genetic variation across this range. And so they looked at genetic data and also collected a series of vocalizations from birds across their range in North America and did an acoustic analysis that included principal components analysis. So I'm just going to scroll down to that piece of this study. The long and short of it was that there was genetic differentiation that was significant, and also the acoustic data supported that pattern in the genetic differentiation for the two North American subspecies. But this is how one might take measurements on sound data. So here are some examples of Pacific wren songs in the West, or what used to be called winter wren, troglodytes, the winter wren pacificus subspecies. And you can see these spectrograms. You can see that this bird, this species, has a repertoire. So depending on when you're taking your recording and what individual you're taking your recording from, you're going to get variation in the way this song looks. But you can take measurements to say something about patterns in the data overall. And the types of measurements people take on acoustic data might be the duration of the song. So if you look at the x-axis here, the x-axis on a spectrogram, which is what we're looking at, is time. And so I might just look at how long each song lasts from beginning to end and get an estimate of how long their song typically tends to be. You may also take measurements of the pitch of the song. So you might look at the highest pitch that the song reaches, and as well as the lowest pitch. They call that frequency, and it's measured in hertz or kilohertz. And so you can measure those points. You can also measure the point at which the pitch at which the sound is at its loudest. And that provides some information as well as what we call the center of the pitch. So the center frequency, what the average is or the median is, depending on what you want to measure. You can also look at numbers of song phrases in the song and numbers of song phrases over the duration of the song. You can look at the numbers of notes in a song and do that, control for that by the duration of the song. So how fast or slow is the song? How many times is the bird varying its pitch from high to low, from high to low? All of these things can be measured and then analyzed. So these are your Pacific wren songs. And then down here we have a range of the songs of the winter wren in the East. And so you probably can see that there are differences. One of the first things that stands right out at me by just looking at these images is that these Pacific wrens seem to be going high and low in pitch to a greater degree than these birds in the East. So people collected these measurements on a range of birds across, on the wrens across their range, and then ran a principal components analysis. So you can imagine each line of the data set being an individual bird that was recorded and its vocalization, and then lots of columns of data. And the columns were the length of the song, okay, the minimum frequency, so the lowest pitch that you would hear in that sound, the maximum frequency, the highest pitch, the mean, so the average, if you average the highs and the lows over the song, what was the average? The standard deviation of frequency. So a standard deviation in this case tells you how much variation from that mean you find in the song. And so in the specific wren songs, for example, I'd expect that number to be larger than in the eastern birds. The percent blank, so this is interesting. So they looked at how much space was unoccupied during the duration of the song. So you have elements of a song, song phrases. A bird might pause between its song phrases, and you would measure that empty space to see how that might vary. And then a number of changes from high to low pitch per second. So they collected those measurements, ran a principal components analysis, and they present here 3 principal components. And so this is 1, 2, 3, 4, 5, 6, 7 variables, and using 3 principal components to explain a pretty large amount of variation in the data set. I'm just rounding here. The first principal component is close to 40%. The second is close to 20%. So it's a little less because we have to subtract, but it's in the 55+% amount of variation of the whole sound data set is explained by the first 2 principal components. And then another fairly large percentage in the third principal component. And so that can be really useful. You can do something like this up here. You can plot your vocalizations, your recordings, just by the first principal component. And so the way this graph is working is it's plotting from west, it looks like, to east, or actually from California, Oregon, and some other locations in the western variety of the wren, and then these locations in the eastern variety, plotting them by principal component 1. And you can see that there is this nice differentiation between the sounds. Another useful thing in principal components analysis, and this is the kind of data, I got to skip back to this kind of information, you could take your first principal component and actually run an analysis of variance on that principal component to see if there are differences between the eastern form and the western form that are significant. Actually, that would be like a t-test in this case. And then you can also gather some more information by looking at what they call component loadings or factor loadings. And so this is part of the output you get in the principal components analysis, is you'll get the how much variance is explained by each principal component. And then you'll also see how each measurement is what they call loading onto that vector, okay, onto the principal components. And these numbers range from 0 to +1 or -1. And the scores that are closer to plus or minus 1 are loading more heavily on the principal component that you're looking at. So in the case of the first principal component, a lot of what's being explained across that principal component is the maximum frequency and the mean frequency. And so the highest pitch and the middle pitch, that's providing the most explanatory power in that data set. And if you, again, look at how these data are plotted, you find that the Pacific forms have a higher, if you're thinking about those loadings, the mean pitch and the maximum pitch, you're finding them in the higher end of this range, with the eastern birds having a lower range for the maximum pitch and for the average pitch. And if you just go back and visually inspect this data, you can actually sort of look at these scales of data on the y-axis, and you can actually see just descriptively that what you're seeing loud elements of these vocalizations pretty high up towards 8 kilohertz. Whereas in the Eastern version, there are some higher notes, but they're not making sounds up there as loud as often during the duration of the song compared to the Pacific Rinds. Okay, and so, and if you look at principal component 2, then you're not going to find the same things, the same measurements loading usually strongly on principal component 2, because principal component 2 is uncorrelated to the first principal component. And in principal component 2, it looks like the amount of blank space said something about that variation in the songs, as well as the standard deviation of frequency, so the variation in frequency of the sound. So there was some range that you could see on a scatter plot where you would be looking at the differentiation between how much blank space is in the song and how much variation there is from high to low. So those are some ways you can use principal components analysis to understand a complex data set. And then you can also use the output, the actual data set with the principal components in them, to run analysis of variance or regression or multiple analysis of variance and a variety of other hypothesis testing statistics.